All right, today we are diving deep into the engine room of modern AI. We're going to uncover a pretty fundamental secret about softmax attention. The mechanism that really makes models like GPT-4 so incredibly powerful. So let's just kick this off with a question that honestly plagues anyone working with large-scale AI. Why is the best stuff always so slow? It seems like the bigger and more powerful our models get, the slower and more expensive they are to run. But what if the reason for this wasn't just some engineering problem, but a deep mathematical secret that we've all been missing? At the heart of this whole trade-off are two competing methods. On one side, you've got softmax attention. It is the undisputed champion of performance, of accuracy, but its computational cost grows quadratically. And what that means is, if you double the length of your text, the processing time pretty much quadruples. It becomes a huge bottleneck fast. Then on the other side, you've got linear attention. It's the light-rate contender, super fast, very efficient, but it just consistently lags behind in accuracy. For years, the AI community has been trying to bridge this gap. And that gets us right to the core of this whole thing. Why, exactly, is softmax so much better? Why can't these faster, linear methods ever seem to catch up? I mean, the gut feeling has always been there, but a really precise mathematical explanation? That's been missing. Well, a recent paper offers a huge breakthrough by just reframing the problem entirely. Instead of trying to build yet another faster alternative, these researchers decided to treat this performance gap like a mathematical mystery that was just waiting to be solved. Their main clue, their starting point, came from a really simple but brilliant idea. What if they could deconstruct the exponential function that sits at the very heart of softmax attention? Instead of treating it like this single, unchangeable black box, they decided to unpack it into its most basic, fundamental building blocks. And to do that, they pulled out a really powerful mathematical tool called a Taylor series. You can kind of think of it like a universal blueprint. It lets you take any complex function, in this case the exponential in softmax, and represent it as an infinite sum of much, much simpler, more manageable pieces. And this is where we get to the big reveal. Because when the researchers applied this blueprint to softmax, what they found really fundamentally changes our understanding of how attention actually works. And this diagram just shows the incredible result. It turns out that every single term in that Taylor series expansion, it acts like its own simple recurrent neural network. So what that means is that softmax attention isn't one single calculation. It's actually an infinite alliance of these simpler networks all working together in parallel. Each one of these pathways you see is just another layer of complexity, another piece of the puzzle.
So here's the crucial point, the real kicker. That so-called fast linear attention that everyone's been trying to improve all these years, well, it turns out it's just the very first, simplest component of this entire infinite series. It's the n=1 term in the grand equation of softmax.
If we look at the diagram again, we can finally see that performance gap with perfect clarity. Linear attention, right here in the red box, is just the first link in an infinite chain. It captures simple first-order relationships, sure, but it completely misses all the higher-order interactions. The quadratic, the cubic, and all the infinitely more complex relationships that the rest of the softmax series is modeling. That's where all the expressive power is coming from. Of course, a theory this big needs some serious evidence. So let's take a look at how the experiments actually validate this new way of looking at softmax. Okay, so this first graph, it pretty much just confirms the problem we started with. That red line, that's standard softmax, and it consistently gets a lower loss, which, means better performance, than all of its linear competitors. There's that clear, persistent gap we've been talking about.
But this is the real proof in the pudding. In this experiment, they started with a basic model and then just started adding more terms from the Taylor series, the second-order term, then the fourth, the sixth, and so on. And as you can see, with each new layer of complexity they add, the performance just steadily improves, getting closer and closer to that blue line, which is full softmax. By the time they get to the 10th term, the approximation is almost identical. It's amazing.
But the researchers didn't stop there. They also turned their attention to the other part of the softmax equation, that really complex denominator. For years, everyone just assumed it was essential, but they had a different hypothesis. What if its main role was way simpler? What if it was just there to stabilize the output, to keep the numbers from going crazy? And the data proves they were absolutely right. In these graphs, they swapped out that complicated softmax denominator with a simple, super efficient vector norm. That's the purple line. And just look at how closely it tracks the performance of the original softmax in green. It's almost identical.
This pretty much confirms that the denominator's main job is just normalization, and we can replace it with something way more efficient. So the mystery is pretty much solved. Now let's break down what these discoveries really mean for the future of AI. So what does this all mean? Well, the huge takeaway is that Softmax's power isn't some kind of magic. It comes from its ability to model this infinite number of complex interactions. We now know for sure that linear attention is limited simply because it only ever sees the very first simplest piece of that puzzle. And finally, that complicated denominator we all thought was so essential, turns out it's really just a stabilizer, and we can replace it with something much, much simpler.
In the end, the performance gap wasn't just some small engineering detail. It was really the difference between using a single, basic wrench for every single job, which is what linear attention is doing, versus having an infinitely versatile toolkit with specialized tools for every single conceivable interaction. That is the secret of Softmax.
This new understanding, it doesn't just solve an old mystery. It blows the door wide open for a new wave of innovation. By knowing exactly which parts of Softmax give it its power, we can now ask the most exciting question of all. Can we finally build a new attention mechanism that has the infinite power of Softmax, but with the speed and efficiency we've all been searching for?